Dear friends, welcome back to the channel, and in our today's tutorial we are going to look at the second form of regression, where we are involving multiple independent variables to make a prediction. So as I said earlier, regressions allow us to make predictions, and it's a form of machine learning, very simple but effectively powerful. And in that context, I want us to look at some transportation data. And this data have been obtained. It's called a trip generation data for a metropolitan area. And it has got several columns. The first column is the zone, which is basically the zone of the area. The second column is the dwelling unique number, which I don't think if it's going to be important for our today's discussion. And the next important variable in this data set is the number of persons. So these are the number of persons in a household. And then the next one is the number of vehicles. So the number of vehicles per household. So if the house has got 3 vehicles, maybe the husband, the wife, and the kid has a vehicle, then there'll be 3 vehicles. And then licensed drivers. So these are the number of people who have a valid driver's license. It might be more than the number of vehicle. And then full-time workers. So these are the number of people in a household that are working full-time. Part-time, number of people in the house that are working part-time. And then work at home. These are basically people who are working from home or remote workers. They are not going to, or they're not driving to work. And then you have got the number of students. So these are kids in the house that are at a school age. They might be going to elementary school, high school, or college. And then we have got the number of females, obviously number of males too. And then we have got the number of children. So these are children who are below the school going age. And then we have got the number of adults, basically 18 and above. And then we have got the daily work trips. So these are trips that are generated by people who are going to work. So if there's 5 people in the house and 3 of them are driving, 2 of them are working, but 1 is a student, then each of these 2 people, if they're driving to work daily, then they're generating at least 4 trips, because 1 trip going to work, 1 trip coming back. That is for a single person. And then the second person, 1 trip going to work and 1 trip coming back. And then the student doesn't count as a work trip. That's a daily non-work trip, which is the last column. So this is the brief description of the data set, and this is what I want us to use to model do our projects for today. So I'm gonna work on my GitHub repo or GitHub directory, and I always work on this directory called the technical, which is my GitHub account. And then I'm gonna create a notebook and name it transportation. You can name it the way you want, so I'll do multiple regression for transportation data set. So that's it. And usually we will start with the basic libraries that we're gonna use. So I'm gonna just make quick comment here: import the necessary libraries. And the first one obviously will be import OS to allow us to manage our files and directories. I'll import numpy as np. I'll import pandas as pd. And then I'll import matplotlib, just in case I want to plot anything. matplotlib.py plot as plt. I'm gonna import cbon as sns import, and I'm gonna use stats model library to perform regression. And we did this in our previous tutorial, so you want to check it out if you're not conversant with stats mod. It's a good library for performing simple regression without necessarily using advanced ones like TensorFlow or scikit-learn. So this is, I think there's an error. It's supposed to be starts models. I think that should work. Okay, so the next thing is to import the dataset. Import dataset. So I've provided the link to the dataset on the video. So please, first of all, let's define the data path of my. So I'm gonna use the OS function called path.join, and here I'm just gonna provide the folder where my dataset is. So you can see my dataset is in the folder called data here, and this is the dataset that I'm looking at, tripgeneration.csv. So I'm gonna do that, specify the folder and the name of the dataset, which is tripgeneration.csv. I've provided this dataset on the link below. Please check it out. And then I'm gonna read it, which is like, you should be conversant with this by now. Can do auto tab to autocomplete, and then input the dataset which I've already defined above, data path. And then for purpose of confirmation, I'm gonna just check the first 5 columns to see if it has read properly. My dataset is read properly. So now let's kind of form, let me say, ad hocly research questions to help us with this. So I'm going to perform basically multiple linear regression. In other words, I'm going to use these independent variables to predict a dependent variable. So what I mean by that is each of these columns represent a feature or the characteristics of the dataset, which can be used to predict an output. And in this case, it will be the daily work trips and the non-daily work trips. And then at some point, I would love us to calculate the total daily trips, which will be just a summation of the daily work trip plus the non-work trips. So to that extent, let me just, and feel free to come up with any research question, but I'm using this for the purpose of the video. So what are the key? I'm going to focus on the daily work trips first. What are the key determinants of daily work trip generation? So in other words, what is greatly contributing to these work trips? Is it the number of students in a house? Is it the number of people working from home? Is it the number of males? So that is what I'm focused on that. And then I will do the same for non-work trips. So I'm just going to copy the same. So I'll say daily non-work trip. And then lastly, and this is where I want us to do something different, it's going to be, what are the factors affecting. These questions look simplistic, but for the purpose of this video, I think we can work with them. What are the factors affecting the daily trip generation, or should I say total trip generation in a metropolitan area? Make this a markdown, and then we are free to go. So the first thing, I just want us to print the columns so that I can copy them instead of trying to type them. So all these are the columns in the data set. We are not going to use each one of them. So let me answer this first question here. Make it a subheading and perform multiple regression based on this question. And I will call this my model multiple regression model 1, and here I'm focusing on question 1, which is daily work trip. Good. So to answer this question, we'll need to select some variables, and this is where now subject domain comes in. In other words, you have to have some kind of idea of some of the factors you think would affect the daily trip generation. So how do you come up with this idea? Basically, look at the features of the data set, and we have got different features here. I don't think if the zone matters so much. The dwelling unit is basically a function of the zone, but the number of persons, number of vehicles, licensed drivers would in some way affect the work trip generation, but you don't want to have so many factors. In other words, you don't want to create a model that overfits your data set. You want to create as generic model as possible that can be applied for a new type of data set. So in my case, I would think the first thing I will do, I will select, for example, the number of people who are working at home, or not necessarily working at home, but the number of full-time workers. I will select that. I will select the number of part-time workers, and probably remote workers, and just this is just for experimental, and I can justify that the rationale for me selecting the number of work person is it directly influences the amount of work trips. So these are the number of people who are working from home, but sometimes they might travel out. That is just an assumption which is not necessarily true. And again, I said this is where domain expert comes in. People who are expert in transport or traffic modeling. And then I also look at the full-time workers, because a full-time worker will likely travel from, in the morning, travel from house to the workplace, and then from workplace back home. The same will happen for a part-time worker. So with this, I can use all those. Let me just take the three variables: work at home, full-time, and part-time workers, and then use that to predict the daily work trips. So in other words, based on these three variables, I'm going to see how they relate to the work trip. So to do that, first of all, let me specify the dependent variable. So the dependent variable is what depends, or is the output based on the features. So obviously the dependent variable is what we are predicting here, which is the daily work trips. So I'm going to do that, create a variable called y to select that, and you can see this is what I mean. So it's basically selecting all the values of the work trips, and then I'm going to create the list, select the independent variables. And since this is a multiple regression, I'm going to select several multiple variables. And I've said the first one that I selected was full-time workers and part-time workers. So let me just copy those ones here. And then also the number of work at home persons. So in other words, the number of people in that house that are working. So these are the three variables. Now I can print that too to see if it is selected correct. So these are the independent variables. In other words, the number of full-time workers doesn't depend on the number of part-time workers, and so is the number of work at home persons. Now the next thing, I need to use this library here to model my data set. And the first thing I'll need to is to add a constant, which is basically a bias term. In other words, I'm going to try to predict the number of daily work trips when I'm not given any of this. So that will be equal to my x-intercept. In other words, if you draw a line where it cuts the y-axis value will tell you the daily work trips whenever we don't have got any value of full-time workers, part-time workers, or work-at-home person. So it's normally in machine learning lingo, it's known as the bias term. So to do that, let me create the bias term using the stats model library, and you can do that by just saying, using the function add constant. It should add automatically. Constant, and this is based on the x values. So I'm going to create a random constant or a bias term, and then now I create a model that I'm going to fit on my data set. So the model is going to be SM, and it's the linear regression model, OLS, and it takes in y value, which is the dependent, and then the x value, which is the bias term, and then fit into a variable called results. So I'm going to do the model to fit in my results. So I'm going to do model fit, and once I do that, I just need to print results, which will give me a summary of statistics for my results. So I'm going to do results dot summary, and it's going to give me a bunch of statistics, including the R square, which tells me how well my model is performing. So if the high square, R square, the R square ranges from 0 to 1, or basically from 1 to 100%. So if you have got a 1 R square, it means your model is really performing well. If you have got it closer to 0, or closer to 1%, then it means your model is performing really bad. So let me see the regression model. You can see my R square is 4.81, and after it has been adjusted, taking care of these other multiple variables, it's still 0.481. But for the time being, I want us to look at this column here, which is very, very important, and it will come up in the later stage of this tutorial. Look at the T, which is the t-test. I will explain what t-test is, and also the p value, which is basically a function of t. So I will explain this, and they're going to be very, very important in this multiple regression modeling. So that is, you can see, look at the values of full-time and part-time. It has got very high t-test values, and of course they have relatively lower p-values, very, very smaller than 3 decimal places. So that will come very, very in handy when you move into the next phase. So in summary, I can say these variables are very key in predicting the daily work trips. So you can sum this in your report. And then the next part is focusing on the second question, which I will use that as my second model for second multiple regression model. So let me do that here. It's gonna be, should be 1, and I'll say this daily non-work trip. Make it a markdown, run it. Here we go. So now in this section, I'm going to create a model that can be used to estimate the total number of non-work trips. And the assumption that I'm going to make is that students are the major contributor of non-work trips. And why? Probably because if you're a student and if you're in a house, the highest number of people who are likely to make non-work trips are those going to school. Apart from, of course, daily chores like going for groceries or visiting a pharmacy or just visiting a restaurant. So I'm going to assume that students are going to be very, very important. So the first independent variable I'm going to select is the number of students. And then if these students, they don't have a driver's license, then it's very, very important to include the number of people in the house with the driver's license. So that's going to be my second variable. And additionally, I'm going to consider the number of persons in the house. So this is going to be my third variable. So the assumption is that the people in the household, if there are more people in the household, then the chance of having students and licensed drivers are likely to be high, and that affects the daily non-work trips. So same procedure. First of all, define the independent variable. So the dependent variable, I mean, which in this case now is, I'm focused on the non-work trips. In other words, trips made not for the purpose of work, but maybe for groceries, for school, things like that. And then X is going to be the set of my dependent variables. So the first one will be, as I said, I'm going to focus on the number of persons in the house. So the total number of people in the house, because I believe this directly affects the number of students and the number of the chances of having a licensed driver in the house. The next thing I'm going to have is the number of licensed drivers. And then lastly, which I think is very important, is the number of students in the house. So as the custom, let me add the bias term to the dependent variables. So I'll do that using the stats model, add constant function. And I'm adding that to the dependent variable. And then I'm going to create the model using the OLS function of stats model. And the input is the dependent variable first, which is y, and then the independent. And then I'm going to present the results by fitting the model in my data. Then the last thing, I'm going to print the results. So here we go. And this gives us the regression results. So now you can see that it's really performing poorly. 33, which is a very, very low value. In other words, this is not a very, very much useful or meaningful model that we can use. But then again, please feel free to interchange these variables so that you can at least have an R square of around 50. This one is definitely low, but in some cases, it's always like this. I know in tutorials like this or in machine learning books, you will find very good R square values, but in reality, these are the kind of R square results that you do get. But I want us to look at the t-test values here. You can see licensed drivers has got the highest t-test, followed by the number of students. So in terms of selection of the dependent variables among our whatever we selected, it means licensed drivers and number of students are very, very key in modeling these results. So that is to do with the second question, but I will challenge you to try to alter these variables and see if you might be able to get very good results in terms of the R square. That will be a good test. I will have tried to do it, but I don't want the video to stay longer. Now, the next thing is to respond to the last question, which is this. So I'm going to combine the two and see if I can come up with a very general model that combines the variables from daily trip model and non-work trip model. So I'm going to come up with that one generic model for that combines the three aspects. So So this one will take both the variables that I've used in the daily work trip and those that haven't used, those that I've used in the non-work trip variables. So it will be based on the combination of both the variables. And to generate this model, the various variables from each of the models, I'm going to combine them together. And then I'm going to select them based on the t-test values. And I want you guys to know what is a t-test value. So if you look at the results that have been printed here, there's t-test. And t-test is a very useful statistical tool, and is basically a comparison, or is a ratio between of variance between groups and variance within groups. So if you take, let me think of a good example. If you try to compare the speed of the maximum speed of cars, or the average speed of cars, let's say you are focusing on Ford, and you try to compare the average speed. Let's say that the average speed of Ford cars is 34, or maybe something like 50 miles per hour. And then the variance within that sample that you have collected is maybe, it ranges from the average, the variance is 50, but the average maybe ranges from 48 to 52. So the difference is basically within that group of Ford cars that you have sampled is 4, because your variance is 50, your average ranges from 48 to 52. So 48 minus 52, that is 4. So that is the variance within that group of Ford cars. If you compare them to the other group of, let's say, Ford trucks, which the average speed maybe will be something like 45, and the variance is from, the average speed is from 42 to 47, then the difference, or 43 to 47, the difference is still 4. So again, the variance within the Ford trucks is 4. So both of them has got a variance of 4. But now the trucks, the variance is 45, the cars is 50. So the difference between the two groups now is a difference of 5. Now the t-test will be simply the variance between the groups over the variance within the groups. So as I said, within the group is constantly 4, but between the two groups, the trucks and the cars, is 5. So 5 divided by 4, you'll get a very huge t-test. So that is how you calculate t-test. But then what does it tell us? So if we have got a t-test value of, let's say, 3 or 5, then it means that the groups are 2 times different, or let's say 5. Then it means if a t-test is 5, then it means the groups are 5 times different from each other, as they are within each other. So if you have got a t-test value between Ford model cars and Ford model trucks of 5, then the t-test is 5. It means the groups are 5 times different from each other. In other words, they are 5 times different. The trucks are different from the cars 5 times, as they are within themselves. And how do you know if this difference is significant? Or how do you know if a t-value is big enough to show a difference? So it happens that for every t-value that we have, you can calculate a corresponding p-value. So if you look at this result that is being showed here, you're going to see t-values and p-values. So the p-value is basically the probability that the pattern that you are seeing on your data set is not produced cannot be produced by any random data. So sometimes you might see a pattern in your data set, you think that, okay, this is very interesting, but it's just noise, or it's just a random pattern. So in other words, a p-value will tell us if the difference in our group is real or is just a fluke in the data set. So we have to test for that. And usually, if you have got a p-value like 0.1, then it means there is a 10% chance that you will get those results in a random data set. If you get a p-value of 0.05, it means there's a 5% chance that that pattern that you're observing in that data set, you will get it on random data. So in most research, the cutoff value for a p-value is normally 0.05. or below. So if you get 0.005 or below, then it means it's not random, it's not by chance, so you can take those. So look at this, our data set here. You will see that we have got p-values that are literally below 0.05, so it means it's not random. But if you come at this point here, we are observing the same. And then how do you know which one to select? Because my values here doesn't give me to fifth decimal place. So I might equally use the t value to select the three or some of the best variables to consider in this combined model. So having looked at the first one here, I will settle for full-time workers and part-time workers, and also workers at home, because I cannot tell from this. And then in the second model here, I'm gonna select licensed drivers, and then the number of students simply, and I'm gonna leave out the number of persons. Why? Because it has got fairly smaller t-values, even though I cannot tell the p-value, but it has got fairly small t-values, but it doesn't hurt. We can include it and see how our regression model performs. So allow me to do that. I will specify y value. So y value, I'm focusing on the daily work trips. So I'm modeling the daily work trips because I think this is like very, very important, especially for modeling the traffic flow in a metropolitan area. And then the x values. So I'm going to select those that I think are of significance. So as I said, I'm going to select all these from the first model. And then I'm going to select the number of licensed drivers and the number of students. So that is my x. And then calculate the bias term using the add constants function. And then create the model that accept the dependent and independent, and then fit the model and assign it to a variable name called results. Model dot fit, and then print the results. That's summary. So I'm getting an error. Let me see. Work daily trips x. Okay, so this should have the data frame added here. Then this should work. So you can see we have got a very improved R squared from here we had 33. Now we have got an R square of 48, even though if you compare it to the previous one, it's just a slight improvement, 48.1. So this is now our generalized model. So this is how you can make a global model that allows us now to predict the future traffic of this metro area. I want us to try something. Let's add to generate total trips, and I said we can find the total trips by simply adding the daily work trips and the non-work trips, and then create a model for that. So create an empty data frame, which is called total trips, and it's empty initially, and then I want us to fill it with addition So it's going to be addition of work trips plus non-work trips. So this is going to be df. Let me add the work trips first, plus df I'm gonna add non-work trips. Run it. Let me check if it has run successfully. Good. So it's an addition of the daily work trips and daily non-work trips. So 2 plus 9, 11, 3 plus 7, 10, 0 plus 0, 0, 0 plus 3. Good. So that's what I wanted. And then I want us to see if we can predict total trips, or we can create a model that will allow us to predict total trips based on either daily work trips or daily non-work trips. And if you look at this relationship here, the relationship is very, very linear. In other words, if any of these variables increase or decrease, they have got a direct implication on the total trip. So if we include any of these, we can easily predict total trips. And by that design, then we don't need to worry about selecting different variables. So let me just illustrate this. Let me create a prediction model. So my focus is to create a model that will allow us to predict the total trips. But the variables that I'm going to select, I want us to include, first of all, focus on non-work trips. So instead of selecting individual variables that contribute to daily non-work trips, I'm going to select just the variable called non-work trips. And then I will add some few variables that are related to work. So one of the variables that is related to work is part-time and non-part-time workers. So I'm going to add these two variables here in our multiple regression model. And then I'm going to add, I think this should be fine. I don't need to add. So daily non-work trips, clearly, we know that daily non-work trips are generated from variables that are not related at all to work. But then in creation of this generalized model, I want to include also those variables that are related to work. And therefore, that's why I've selected full-time workers and part-time workers. So any of these trips that this group of people generate, it has to be related to work most of the time, not every time. So let me create a bias term for this. So I'm going to do sm dot add constant x, and then create a model sm dot ols, and input the independent variables and the dependent variables. And then I'm going to fit the model and assign it to variable called results. So model dot fit, and then lastly print my results. So results dot summary. So you can see we are really getting very nice regression model that is at 0.93, which is basically 93%. So by just having a proper understanding of how we can generate total trips, we have created a very fairly accurate regression model that will allow us to predict the total trips based on daily non-work trips and some variables that contribute to work trips, such as full-time workers and part-time workers. And this gives us very nice prediction here. Let's try and swap this with daily work trips and see how it performs. So I'll do the same thing, make my y variable to be still total trips, and then x, I'm gonna select a series of variables here that are related to work. So the first one is gonna be licensed, full-time, part-time. Let me select this. All those ones, I've selected those ones. I'm gonna select, let me see, work at home persons, good. Select that too. And then I'm gonna select those that are not related to work. So things like number of children, and also number of students. So for now, let me select number of children. I think it should be like this. Number of children and also number of students. Number of students. And you can try to make different combinations and see if you can improve the accuracy of this. Obviously, I'm doing this because I'm not conversant with the transportation modeling, but it's a good demonstration on how subject domain experts can really help you to improve your model, because they have got understanding of the major variables contributing to this. So I'm adding the bias term, and then I'm fitting the model into the data set, sm.ols. So I'm using the model OLS because I'm gonna fit the ordinary least squares method, and then fit the model and assign it to variable name called results, and then print the summary or summary statistics of my results, results.summary. And this should give me the results that I'm looking for. So you can see I'm having a fairly low R square, but let me try to add any variable here. Let me take work at home persons and see if it can improve. So this is where domain expert comes in. Let me add that and see if right now it's 42. Okay, it has improved a little bit. Let me, instead of doing this, just take the whole of daily non-work trips and see if it's gonna improve my model accuracy. Add it here. Here we go. We are at 93.6. Good. But these non-work trips, I was looking for work trips. So Let me use work trips, not non-work trips. We already done that. Yeah, so this is fairly good. It's at 55.8 and the adjusted one is 55.7. So please, in your time, try to play around with the variables and see how well you can come up with the best model. And yeah, so that will allow you to know how best to model this transportation data. But in summary, we have made 3 models. The first model, we focused on the daily work trip, and we realized that these are the key ones. Again, I challenge you to try different combinations of dependent variables. In the second part, we have made a second model, and we have realized that these are the key dependent variables that affect the daily non-work trips. And then the third one, we basically made a super model that combines both non-work trips and work trips. And of course, we've gone ahead and created a model that will allow us to predict the total trips for that metropolitan area. And based on that, we have got 2 different models: the one that considered the daily work trips, and the daily non-work trips, and the one that considered the daily non-work trips. So this is a quick way on how you can model your data set using multiple regression technique. I've attached all the data sets. I've attached this file or this notebook for your reproducibility. If you have any questions, please feel free to interact on the comment section. Let me know which combinations work best for you and if you could get better R-square results based on this data set. For now, bye-bye.